Okay, section 1.4 is on end behavior, and end behavior should be new for all of you. And the focus of end behavior that we're going to be talking about today is using limit notation. So we're going to be talking about limits, which I believe is new, and representing those using limit notation. So this first example here will just talk us through some of the basics of what end behavior even means, and then how to write that using limit notation. So first I want you to graph this function right here. So use your graphing calculator, and then graph it over here on the axis provided. Okay, when we talk about end behavior, it's super important to be accurate with our graphs. So as you look at this graph, we want to make sure that we graph it correctly. And you'll see right here that it looks like the graph is approaching an asymptote there that's not visible, and another one maybe right here. So the best way to double check that is to go to your table. Now, for some of you will probably need to go to table set. Most of them are probably set to auto. Your independent variable is probably automatically filled. With end behavior, it helps if you can change that to ask, and then you can decide, and then go to your table, which would be second graph. So we want to see what are those values approaching. So you can see when I plug in 1, that's my y value, 10, 100. So you can type in larger and larger x values to see what's going to be happening on our graph. And it looks like it's getting higher and higher, but closer to, never over the value of 1. So that should help understand that that y value is getting closer and closer to 1 as x gets very large, and similarly as x gets very small. And then it looks like there's an asymptote right here where x equals -1. So to double check, you just want to hit trace at -1. And there's no y value there because the function is not defined. So now we know for sure that we've got an asymptote there at x equals -1, and here where y equals +1. So now we can go ahead and graph our function, and we're going to have an asymptote right here and here, and then our function looks like I have a point at 0, 0. Let's try that again. It's hard to be very accurate with a stylus, so hopefully you all can follow what I'm doing here. Okay, so that's what the function looks like. And again, we're looking at the end behavior, and end behavior is exactly what it sounds like. It's what is happening at the ends of the graph. So this arrow down here, what's going to happen at that end, and this arrow over here, what's going to happen at that end. What value does the function approach? And if we look at the end of the graph where the x-coordinate gets very large, so over here, what y value is our function approaching? And we already saw from our table that that's approaching the y value of 1. And then we can look at the end of the graph where the x-coordinate gets very small. So as x's get very negative in this direction, then our function is going to be approaching this other asymptote, same asymptote where y equals 1 again. So that's what end behavior is referring to. It's the y value that the function is approaching at the ends of the function. So there's 3 different ways that we can write about the end behavior of a function. And you'll see these 3 ways listed right here. The first one is limit notation, and this is going to be what I'm going to ask you to use. But you should know how to use end behavior and equation of the asymptote. So limit notation, to represent end behavior, you use the letters LIM. So we're going to use limit notation to describe this end behavior that we just looked at. To do that, you write LIM for limit. Next to the limit, you write the name of the function, and ours is named f of x. So the limit of f of x Below that limit, you write what x is going to approach, because we've got two different limits here. We've got the limit at that end of the graph and the limit at the negative end of the graph. So the limit at the positive end of the graph, we describe it by x approaching infinity. So the limit of f of x as x approaches infinity is 1. So this is describing the end behavior, and again, we describe end behaviors using limits oftentimes. So that's all I've specified here is what happens at the positive end of the graph, so we would need to write at the negative end of the graph as well. Same thing, I'll write limit LIM, then the name of my function, so the limit of f of x. Below that, I'll write as x approaches negative infinity, and that equals also 1. So those are my two different limits that represent end behavior at both ends of my function. Now, because these limits are the same, I could have written that all as one limit. Let me try. I'm going to be short on space, but I could have written that as the limit of f of x as x approaches positive and negative infinity. So you can write it all as 1, only if they're the same on both ends, and then I would write equals 1. So that is limit notation. There's two other ways to represent that exact information. The next way is end behavior notation, which is confusing because we already described the end behavior with limit notation, but end behavior notation is just closer to how we say it in English, not using the actual word limit. We're just going to say, write out in words what's happening as x approaches infinity and negative infinity. So using end behavior notation, you write out as x approaches, so that arrow means approaches, infinity, comma, and then you write what the function itself does. F of x approaches, so arrow 1. So we've only described the positive end as x approaches positive infinity, so then you would just write the second half of that end behavior, writing as x approaches negative infinity. And then write f of x approaches 1. So that's another way to represent exactly what we just did using limit notation. The third way to represent end behavior is just writing the equation of the asymptote. End behavior will always be, if it is limited to a specific value, in this case 1, there will always be a horizontal asymptote there. So any horizontal asymptote will be used to describe end behavior, and that's an important note. So horizontal asymptotes is always going to tell us that. We'll just do that. So the horizontal asymptote that we saw was right here where y equals positive 1. So we could also represent it with that equation, y equals 1. Okay, moving on to the next example. We're just going to kind of practice what we just talked about. So graph this function on your graphing calculator and then sketch it over here to the right. So when you see the graph of this function, you'll see that it looks like it's actually resting on the x-axis, but it's not. It's just very close, and then it gets larger and larger. Actually, that's not totally accurate. A little steeper there. So it looks something like that, although it crosses through the 0.11, so it should have gone through that. And then if you're unsure as to whether or not this is going to be bound by a vertical asymptote, you can always go to your table like we did before. But if you do, you'll see that that y value is going to get larger and larger and larger as the x's get larger and larger. So that's our sketch of the graph. And then if we look at part A here, it's asking, looking at the end of the graph where the x-coordinates get very large, what value does the y-coordinate approach? So remember, the end behavior, we're always looking at that y value. What is it getting closer and closer to? So if we look, what this arrow means is that this function is going to continue going up and it's going to continue going over. So the y value isn't approaching a specific value. It's just going to keep going and going and going. So what value is the y coordinate approaching? It's not approaching any specific value. If you want to think of it, what we call that when it doesn't approach a specific value is that it increases without bound. Increases without bound means it's not bound by any asymptote. So basically that means y is approaching infinity. Use limit notation to express that. So limit notation was the first notation we looked at in the first example. So describing the limit notation as x approaches infinity. So we write LIM for limit, and we're taking the limit of our function g of x as x approaches infinity. And we saw right here that that wasn't approaching any specific value, it was increasing without bound. So the limit is infinity. The limit of g of x as x approaches infinity is infinity. And then at the other end of the graph, we can look at what's happening as x gets very small. So we're talking about this end over here. So it looks like it was resting on the x-axis. If you look at your table and plug in values where x is very small, so I'm plugging in negative 100 or even negative 50, you'll get some scientific notation points or y values. That just means our y values are very, 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 very small, and there's always going to be numbers out here. So that means it's approaching 0. So I want to use end behavior notation to express this answer. So that was the second one from above. So end behavior notation is writing out as x approaches, so we're just looking at negative infinity for this piece. As x approaches negative infinity, our function g of x approaches 0. And that's it. So those are the two. We've got limit notation here and behavior notation there. Again, this is what you'll probably be using more of, especially as we get into the calculus part of this class. So if we wanted to represent this using limit notation, we could have said the limit of g of x as x approaches negative infinity equals 0. Those mean the same thing. Okay, over on the next page, interesting cases of end behavior. And these both occur with trig functions. So I have these functions graphed for you already. So really it's just more, this is more about observing what's different about these examples than the other ones. So here we have on example 3 the graph of the sine of x. So this is the graph of sine of x. It should look familiar. We've got our sine wave right here, crosses at 0, 0, the period here between 0 and 2 pi. So if we look at this function as x approaches positive and negative infinity, is the y value approaching a certain number? So we're looking at this function is going to continue up and down, and this is called oscillation, where it goes up and down and up and down, and it's actually not approaching any particular value. It's never going to converge and get closer and closer to something. So this is not approaching a specific value. If it's not approaching a specific value, you might think it's increasing or decreasing without bound, like we saw in the last example, but it's not increasing or decreasing without bound either. It's going back and forth, up and down, between negative 1 and 1. So it's not approaching a specific value. It's not increasing without bound. It's bound by 1. It's not decreasing without bound. It's also bound by negative 1. So the question is, how do we describe that end behavior? And because it's not approaching a specific value, and because it's not increasing or decreasing without bound, a problem like this there is no limit to these functions. So if you've ever seen the Mean Girls movie, this is where everyone gets excited about that because the limit does not exist. So the limit of the sine function as x approaches positive infinity does not exist. So I just write dne for does not exist. And same in the opposite direction, this is going to continue oscillating as x approaches negative infinity, and the limit does not exist. So does the function h have an asymptote? No, it does not. And then if we look down below, we've got another form of a trig function here. This is the function sine of x divided by x. So this is an interesting graph if you take a close look. It starts, it looks somewhat similar in the sense that it's oscillating, or it seems like it's going up and down, but you'll see that those peaks and valleys quickly die down, and you'll see that they start to get closer and closer to leveling out. They will never level out to equal 0, but you will find that they actually are getting closer and closer to 0. So it will never even out. It will always dip just above and just below 0. But it is getting closer and closer, or approaching 0. It's not increasing without bound. We can see that it's getting smaller or closer to 0. It's definitely not decreasing without bound. So this is confusing to people sometimes because you see a function where it is going up and down, dipping above and below the x-axis, but it does still approach a specific value, and that value is 0. So the limit of this function on both ends is still going to be 0, even though it goes above and below 0. Now, this question here, does it have an asymptote? The answer to that is yes, it does, because again, end behavior is always determined by horizontal asymptotes. So if we can figure out this end behavior, then it must have a horizontal asymptote at y equals 0. And that bothers some people because how can a function cross over an asymptote? Well, functions can cross horizontal asymptotes. They will never cross vertical asymptotes. So that's kind of a helpful thing to remember for that one. Okay, next we're going to talk about the end behavior of odd and even functions. So before we even do that, we've just got a quick review on what even and odd functions are. So if you think back, hopefully it rings a bell. That's my only goal, is that it just rings a bell. And then even if you're relearning that, that's okay. So an even function, there's a couple ways you can talk about it. We can talk about the formal definition, and then we'll look at the graph of even functions. And a function is even, so we'll call our function f, if f of x, so any x value I plug in, the y value for that would be the same as if I plugged in the negative version of that x value. Meaning if I plotted a point for positive 2 and it was right there, then the point for negative 2 would be exactly the same. So great examples of even functions would be a parabola centered at 0, 0. So even functions are symmetric about that y-axis, and the y values for any x value are the same as the negative x value. And then we've got odd functions, where if I use f of negative x, that is not going to be the same as f of positive x. Like an even function, it's actually going to be the opposite of f of positive x. So in this case, say I have if I plug in some value for x, and so let's say I plug in 2 for x, then f of negative 2 might be down here. That means when I plug in positive 2, it would be the opposite of the original y value, and it would be in the opposite quadrant. So odd functions. That is a bad picture. odd functions, let's see, this was an f, look like this, except they go through the origin. And they are symmetric about the origin. So this point, I could rotate this whole thing and it would land at its corresponding point in the other quadrant. So even functions are symmetric about the y-axis. You can fold it in half on the y-axis. Odd functions are symmetric about the origin via rotation. So just keep that in mind as we look at the next page. And we're going to look for patterns for end behavior for even versus odd functions, because we will see a helpful pattern in looking at those. Okay, so in this last example, or second to last example, we are given all of these different functions here, a through e, and these are some common power functions. So you'll see different powers of x, and we're going to describe the end behavior of each of these using limit notation. So I will go through the first one with you, and then I highly suggest you pause the video, go through B, C, D, and E on your own, just to make sure that you guys are using that limit notation correctly. And then you can check your work with mine if you'd like. Okay, so first we need to graph a quick sketch, and I mean really basic. All we want to look at, all we need to do with our graph is make sure we have enough information visually to talk about end behavior. So the function y equals 3x, we know that that's going to look like a line. Think of y equals mx plus b, except our b here is just 0. So this function is just a line. And now I have plenty of information here to graph or to write limit notation end behavior, because I have both my two ends, I know what direction they're heading. So if I look at this, then let's talk about as x approaches infinity. So using limit notation, I would write that the limit of this function, so this function isn't named, so I can just actually write the function itself, which is 3x as x approaches infinity. And that limit, since it's increasing without bound, is also infinity. And then I would do the other end, the negative end, as x approaches negative infinity. The limit of 3x as x approaches negative infinity equals, so I'm looking at the y value down here, it's going to continue to get negative and approach negative infinity. So what I'd like you to do is pause here, sketch a graph of all of these other ones. You can just plug them into your calculator, get the general shape, and then sketch it, and then write the end behavior notation next to it, or the limit notation of the end behavior next to it. Okay, so now you can see I filled in the sketch of each graph and the end behavior of each graph on both ends using limit notation. So you can take a minute here and pause or quickly skim through and make sure you've got all of those correct limits on both ends, and also that you used limit notation correctly. Once you've checked all of your different examples, what I want you all to get out of this, the pattern I want you to try and look for, is how the two different ends of a function relate based on if the power of the function is even or odd. So we'll go through these and look at them. This first one, a, it's a power of 1, and we'll see that the limits on the two different ends are opposite. One of the ends is approaching infinity and the other is approaching negative infinity. If you look at b, we've got an even powered function, a power of 2. And then if you look at the ends of the function, both ends are approaching positive infinity. So whether or not x is getting very large or very negative, they both approach the same value of positive infinity. So if you go through and look at the rest, let's look at these two odd functions, 3 and 5. So the third power and fifth power, just by looking at the shape of the function, you can tell that the end behavior is opposite on both ends of the function. So if we know one end of the function, the other end is automatically going to be opposite of that. And same with x or negative x to the fifth. They are opposite of each other. And then likewise looking at the fourth power function, this, because we've got a negative coefficient out front, they're both approaching negative infinity, but it's the same value for each. So the important takeaway from this is if it is a power function, you know one end of the end behavior just from, if you know one, you know the other one. So the important takeaway from that, if you can understand my rambling, is that even if it's an even function, you have same end behavior. I'm just going to write EB for end behavior. And then if it is an odd function, odd, it's opposite. So that's a helpful tool in analyzing different types of power functions. All right, one last example here, and this kind of just recaps what we've learned about end behavior and then what we've specifically applying end behavior to even and odd functions. So I mentioned on the last page that an even function is symmetric with respect to the y-axis. So you can think of folding the y-axis in half. So it is symmetric with respect to the y-axis. Which of the functions in this section of notes are even functions? So you can pause right now, go back, and just list all of the functions that we looked at that are symmetric with respect to the y-axis and therefore even functions, and just list those here. So those functions I've just listed. Obviously the two functions from just above with even powers are going to be even functions, but you still do need to make sure that those are symmetric with respect to the y-axis. And then on the previous page we saw that the function sine of x divided by x was also an even function. And then I want you to do the same thing for the odd functions, and those odd functions are symmetric with respect to the origin, which is the center of a graph 0, 0. And now you can go ahead and look back and identify all of the functions that we've looked at in this section of notes that are odd functions. And those are all the odd functions that we saw in this section of notes. And again, when checking for if a function is odd or not, it won't always have an odd power like these do and this one. Y equals sine of x is an odd function because it is symmetric with respect to the origin. You could rotate it around the origin, so that is an important piece of that. These next examples are just to get you thinking about end behavior of an even versus odd function and thinking about conceptually what that means. So if an even function contains the point AB, then it also contains the point what? So remember, we saw that even functions were symmetric with respect to the y-axis, meaning if I used a specific x value, in this case a, that would mean when I plug in the negative of that, so negative a, I would have the same output of b. So now we're looking at how that translates to just looking at coordinates of a point on an even function. So the next would be similar, but now we're talking about an odd function. So if I have an odd function and it contains the point AB, then it also contains the point what? And that was opposite of what we just talked about with even functions. So in this case, if I plugged in the negative x value, so negative a, I didn't get the same exact y value as before. I got the negative version of that. So if an odd function has the point AB, then it also contains the point negative a, negative b. So think of that looking at a function. If I had 1, 1, then it would also have negative 1, 1. And then these two down here, E and F, if F is an even function, Remember, even functions have the same end behavior at both ends. So if the limit of f of x as x approaches positive infinity is 3, then what is the limit of f of x as x approaches negative infinity? If it's even, then it has the same end behavior, so it's going to be 3. And then lastly, if f is an odd function, and I know the limit as x approaches positive infinity is -5. Remember, odd functions have opposite end behavior. That means as x approaches negative infinity, the function will approach the opposite of -5, which is +5. And that's it on end behavior. One quick note, when you look at your homework, you'll see a small change in notation on some of the examples, not all of them. I taught you that this is how you write limit notation, and that's correct. But due to being limited on Microsoft Word with math symbols, you'll see some of it written out like this. Instead of x approaches infinity below, you'll see it right next to it in subscript. That means the same thing. I just couldn't get that below the limit. So this means the same thing as this, but this is how you should write it if you're writing it out yourself.